adult, and the red spot just there is a varroa mite. This is one in the pupation stage, and as you can see here, there are 2 varroa mites here there. There's various other parasites as well, and predators, for example, the Asian giant hornet, they can devastate honeybee colonies because they kill them, they bite their heads off, and various other insects as well that feed off bees. Various pathogens, such as bacteria, such as the 2 foul broods, and various viruses tend to damage, harm, and if not kill bees. Possibly bees are becoming less resistant to pathogens such as these diseases, possibly due to lack of genetic variety because they're bred for honey production rather than robustness to disease. As we see here, particularly in the USA, there's large areas of what we call monoculture, where one crop is grown. So in this part of California, almonds are grown almost exclusively. So they flower in what is the Northern Hemisphere very early spring, around about February, in California anyway. And so bees are shipped in there to pollinate the almond plantations, but there's no, in terms of agricultural crops anyway, very little by way of other flowers for the rest of the year to them to live off. Also, maybe because of excessive harvesting of honey, there might be bees dying from malnutrition. Also, in intensive agriculture, excessive use is made of chemical pesticides and fungicides as well. They are believed to be harmful for bees for their feeding cycle, and these probably are detrimental to bees. And possibly things like climate change also probably have a factor. And some reports have even suggested that mobile phone signals are harmful to bees as well. So some of the problem about the way bees are kept to support this agriculture is possibly questionable as well. In America, as you see here, beehives are shipped around the country. This is the continental USA, so California is over here. The New England states such as New York, New Hampshire, and Maine are up here, Massachusetts, and down here is Florida and Louisiana. So they're shipped around the country to pollinate particular crops, shipped around on great big trucks like this one. And so that's possibly stressful for the bees as well. And also they don't encourage the bees' natural breeding cycle, which probably reduces genetic diversity and may reduce resistance to pesticides and diseases. Excuse me. As I mentioned, some studies have suggested that mobile phones and other forms of electromagnetic radiation may be harmful to bees as well. And this study is actually from India, suggesting that bee reproductive productivity could be greatly reduced after exposure to mobile phone signals. So, well, what can we do about it? Well, we can promote bees primarily for pollination. That's important both to the agricultural sector and to the wider natural environment, and encourage better diversity of vegetation, so wildflowers and that in amongst crops. That would provide the bees with pollen and nectar for more of the calendar year. Maybe limit honey harvesting, because honey is a natural food for bees. Beekeepers tend to feed them sugar water or fructose syrup in the winter, which isn't necessarily the best for the bees. Encourage their natural breeding to improve genetic diversity, and minimize disruptive inspections of beehives. You do need to do them to guard against disease, but also over inspection can lead to actually disease being spread from one hive to another by the beekeeper. But you do need to maintain some sort of monitoring in order to check for deadly infestations of things like American foul brood, which would completely ruin a hive and put neighboring hives at risk as well. Okay, so Have I missed something out? No, it's all right. So we're acquiring signals from beehives. So I wanted to illustrate some of the mathematical and other methods that we'll make use of in this analysis. And if X is a time sampled signal, so it's actually measured at regular time intervals, that's what X of n is. So X of n is a time sequence measured from a signal. So X of n is the signal at time step n, and tau, the Greek letter tau here, is a time lag. So you're comparing the signal itself with a time delayed version of itself. And this mathematical formula gives you the autocorrelation function. You can normalize it to make sure it's between +1 and -1. N is the number of samples that you measure in a particular window, a cycle, if you sampling cycle. And this can be used to detect periodic repetitions within a signal. So when this value is close to 1 at a particular time lag tau, that means that the signal is almost identical to a time delayed version of itself by that amount tau. If it's close to -1, then it's almost completely out of phase with the time lag version of itself. Excuse me, my voice is a little bit hoarse, so I'm just drinking some water. Cross correlation is a way to compare two signals, allowing for a possible delay in one of them. And we've got an example here. It's very similar to the autocorrelation, except you're multiplying a signal by a lagged version of the other one. And I think this is for two signals, one of which is the temperature, the ambient temperature, and the other one is the level of daylight. So this is a common thing, that the level of daylight tends to lead the temperature signal, because the sunlight has an effect of warming up the environment, but it takes a while to do that. So peaks, it's often quite cold when there's strong sunlight in the morning. The peak sunlight occurs at what would be astronomical midday, but the peak temperature occurs a couple of hours later typically. So there's an example where the cross correlation would show lagged periodicity between two signals. And the lower function in here is the autocorrelation function. So it has its highest value at this particular value of the log lag, which I think in that case corresponds to about 2 hours. So this can help identify both periodic repetitions between signals, but also relations between two signals. Another method that's commonly used is the Fourier Transform that you may have come across, and that decomposes a signal into its periodic or sinusoidal components. So again, X of n is a sampled, a discrete, regular sampled version of from a signal. We sample regularly at a rate of fs samples per second, and so n is a counter, 0, 1, 2, 3, and so on. And the so-called discrete Fourier transform, which is very close to a Fourier series, is defined by this formula, where this is a complex exponential. You may be more familiar with calling j instead of I, where I or j is a square root of -1. The inverse transform to recover little x of n from its Fourier transform big X of k is given by this formula. So the sign of the exponential term is different here. Excuse me. But here we can see that we can decompose a square wave into a set of sinusoidal components, which if we add together, we gradually recover the square wave again. We can also decompose a more complex periodic waveform into sinusoidal components this way as well. So this can give us both information about periodic components in the signal, but also how strong they are. Now, the discrete Fourier transform as it stands is not very computationally efficient, but in 1965, so over 50 years ago now, Cooley and Tukey introduced a clever way that was done by pairing up complex exponential terms over and over again. and that led to a major speeding up of the algorithm. That's called the fast Fourier transform, often abbreviated to